JSPS Fellowship, and UKIERI Fellowship from the British Council of India to initiate collaborative research between leading universities of UK and his organization. Sir has actually there is a huge list. He worked on various optoelectronic devices, emerging optoelectronic technology award, outstanding research work in the area of nanophotonics, SK Mitra Memorial Award for in the best research paper in IETE technical review, and there is so many things. So without delaying, I welcome to our speaker, Professor Ravindra Kumar Sinha, sir, for this
Sir.
starting.
Okay. So thank you, Dr. Upendra Kumar, for introducing me. That is the advantage. Without getting the introduction these days, people get the details about the faculty. And I also thank Dr. Akhilesh Tiwari for contacting me to deliver a talk on this very important topic, that is fundamentals and applications of photonic crystal and metamaterials. Since last so many years, I have been doing a research work in this area. So it is a pleasure to deliver a talk on related to this topic. What I am finding in your list, there are people who are having their prefixes as a professor. Some of them are doctor, and maybe some of them are the students. So that makes the speaker a bit difficult how to give a talk. But nevertheless, I will assume that whatever I am saying, I will be explaining, considering all of you as a layman. Okay, so excuse me, those who have been highly distinguished persons who are attending in this. I will explain in my own style, and considering that I am explaining to first time to you people, and maybe few lectures must have been done. I have seen the list of the speakers. So in 2 days, basics of photonic crystal fiber and electromagnetics involved there on the photonic crystal must have been already been given. And then there are various topics I have seen on the sensor and all. Dr. Jha has given. Maybe my successor, Dr. Professor Anantha Ramakrishnan, who has also been the previous speaker, so he must have explained the metamaterials very well. But I will speak, and wherever necessary, I consider these are the workshop mainly for those who are the first timer or those who want to enter into the field. So with keeping that in the mind, I will start this lecture. Okay. So I'm just sharing my screen. My voice is clear, Dr. Tiwari?
Yes, sir, it is fine.
Yeah. In between, sometimes asking you to Dr. Upendra Kumar or Dr. Tiwari to respond me that yes, the voice is clear or the screen is visible.
Yes,
Okay.
yes.
They have become the new norms of the teaching in this COVID period, that we have to always say the screen is visible, my voice is audible or not. Okay,
Yes.
so I am sharing the screen. Yeah, so the first question, Dr. Tiwari, screen is visible?
Not yet, sir. Yeah, now it is. Now
Okay.
it is.
Yeah, it takes time, the video signal.
Yes.
Okay. So right now it is not in displayed mode. Now I am making this displayed mode. Sorry.
Yeah, it is absolutely fine, sir.
Okay. Okay, so the topic which I have coined for today's presentation is zero index metamaterials, physics and application. I have been already introduced. I am working presently at the Delhi Technological University, heading one of the center. But on the core of it, I do teach fiber optics, or optoelectronics related courses. So we have one center there. So I will start with that light and matter, they interact, and how they are interact that depends upon the light wave, which frequency, which mode, which wavelength, and what type of a material and which material is there. So how, let's say take this as a matter where the light is put onto that is an incident. Depending upon the matter, there is a response. What is the response of the material with the incident of the light? So that response is measured as a material parameter called epsilon, which you all must be knowing. That is permittivity, permeability, conductivity, and the chi value. Okay, so we call it a susceptibility. So these are the material's response. If I change this light wave, maybe material may give me a different epsilon. Okay, it is not constant. So a natural material has this. We call this is the response of the light wave incident on this material. Okay, so these are the material parameter. And epsilon R is epsilon by epsilon 0. That is the relative permittivity of the medium. So you know that the refractive index is related with the epsilon and mu, and it is given by this. So when a light is incident there, what happens in the materials? If it is a conductor or if it is a dielectric or a semiconductor medium, it depends upon the light's frequency. Some frequency will find the semiconductor as a dielectric of the light. Okay, some frequency of the light. Okay, so there is hardly that difference. So there will be some interaction the light will be doing, and their response is given like this. And there is a parameter called the refractive index that is given by this. So it does depend upon the wavelength, polarization of the light, what will be this value. Okay, that is, this light will be experiencing how much is the refractive index. We will be measuring its impact. And during this course, I will define a refractive index on my own way also sometimes. Okay, so this is there. So now what is happening? Let's say you take a material, okay, and in that material, you include some inclusion, okay, various types of inclusion. Okay, what happens when the light is incident, these included material and the host material, they will have some formation of a dipole, okay, and dipole will generate electric field, then they will be interacting. So the material will experience a different refractive index. Okay, different refractive index if you have included. That is, we are engineering the structure by putting some inclusion, okay, in this material. So what will happen? These, how much of the refractive index, the same light wave which we have launched there, it will depend upon the composition of these inclusion, alignment, how we have aligned, how we have arranged them, what is their density, because when the light wave is falling on them, maybe if it is in a dielectric, there also the dipole will be created. And of course, where we are giving this inclusion, in the host medium also. And more importantly, the geometry, shape, and its arrangement. That is how the photonic crystal has come on. How we are giving this inclusion here of a different material. Maybe we can make a hole, a circular hole or rectangular hole, and keep it in an arrangement. And these aspects have taken birth as the fabrication facilities in the nano areas have increased. Okay, then we started with that a given material, let's say you have a silicon wafer. If you shine a light, normal light, many of them will get reflected. But in the same silicon, if you dope something or you put a certain hole, it will not give the same refractive index. Okay, it will not give the same refractive. So effective refractive index each changed. And that we observe means its impact we observe. Like suppose if a light wave is launched in this medium, without inclusion, and after what time it is coming back, that will be some value of n original. But after the inclusion, if we do it, then it will come at a different time. And from there, back analysis, we can find about the n effective. So, in nutshell, what is happening? What is the refractive index of a given material? Okay, at a particular frequency, natural material, we are not satisfied with that. We want to engineer that material, and those engineered materials are called the artificially engineered material. And whatever the n effective we want that it should behave like this n effectively, accordingly the geometry and all will be decided, and it will work like that kind of n effective. Okay, these days we do what type of a field distribution within the material should be there, and accordingly we engineer the material so that the field distribution within the material should be there. And these external capability we have got with the development of a nanofabrication facility, scanning electron microscope, focused ion beam methods, and various laser printing and all like that. So that has given an extra arm. So in nutshell, we can engineer the properties of the materials. What the God has given to the properties, we are not satisfied. We want to extract additional properties. And my topic of the talk is the zero index metamaterial, physics and its application. So I will explain a bit of metamaterial and its classification, how it is made. Okay, that is, if you are engineering the properties of the materials which is not naturally available, and we call it a metamaterial, and I will classify the metamaterial on my own ways, not following the existing textbook. And then I will explain these metamaterial mostly in the early 2000 to 2010 were being made using the metal inclusion. But as you know, the metal at the light frequency, it is a highly lossy ohmic loss. So people try to work and make the metamaterials using the dielectric. Okay, using the dielectric. So I will be introducing all dielectric zero index metamaterial. That is in at optical frequency. Silicon is also a dielectric at an optical frequency. So we call it. So not to be confused that if I'm saying a dielectric and using a semiconductor medium. And how zero index phenomena comes? It comes from the Dirac dispersion, not done by the Dirac, done by another scientist called the Wang and Huang scientist. They have given a theory, but following some points, and they call that as a Dirac dispersion. Rather, it is called accidental degeneracy induced Dirac point, that is ADIDP. For the realizing the zero refractive index, meaning when the light is incident, it should experience the material is having a zero refractive index. So how to design a material which will give you at a particular wavelength of the light zero index medium? Looks awkward few years back, but yes, today we have an experiment, we have it's an application, and of course bunch of modeling papers throughout the world. And what are the applications of zero index metamaterials? Then I will be giving some example called the optical antenna, electromagnetic cloaking. Electromagnetic cloaking is done by the metamaterial. Okay, but I will give another view that zero index metamaterial is more preferable for the electromagnetic cloaking and wavefront engineering. These are main point. And then I will summarize. Also, I will give you the relevant sources of the materials which you should read if you want to develop your interest in this field. And based on the realization of a zero index phenomena, many devices coming. So a new chapter in the photonics is coming. Okay, like we have a quantum photonics. Okay, so similarly, zero index photonics. That is what we can do. So that is the outline. But all these outline of my talk is based on the previous talk. That is how I am engineering the materials. Okay, and the materials which I have engineered so that its property is changed. Okay, we call them as a metamaterials. So metamaterial is an artificially structured material that derive its properties from its structure rather than its constituting material. Of course, it will depend upon the constituting material, but how we have arranged them, accordingly its properties will be there. Okay. And metamaterials are, which you must have been introduced already, but in order to maintain a continuity, I am doing it. They are assemblage of multiple individual elements fashioned from conventional microscopic materials such as metals, dielectrics, plastics, or their composite, usually arranged in a periodic patterns. Not necessarily that it will always be. Generally, while making so that we can model the properties well. So we do in the periodic patterns. We can forecast that what it will be the properties. And most of them in the beginning, it was done by the metals. Again, for a metamaterial, that is when you are structuring it, that is suppose a silicon surface is there and there you are creating a one hole, another hole, then it will no longer be in a homogeneous. It will be inhomogeneity. That is, light will find inhomogeneity. So a material has an inhomogeneity scale. That is, this homogeneity scale will be smaller than the wavelength of the interest. That is, if you are making a metamaterial at a 1550 nanometer, and then you are arranging these inhomogeneities at 100 nanometer, 200 nanometer, then it is well and fine, it will be like that. So in an homogeneity is much smaller than the wavelength of the interest. So precise shape, geometry, size, orientation, and arrangement affect the waves of the light. That is when you have launched, or the sound. We can have a, like we call a photonic band gap material. Similarly, we have a acoustic band gap of material. So any wave is affected by these shape, geometry, size, and orientation and their arrangement in an unconventional manner, creating material properties which are unachievable with a conventional material, which were not achieved in the actual material. So metamaterials, normally in the mind of the people, even those who are learned and who have done the work, they think metamaterial means it will have a negative refractive index. Okay, it has been dominated. That is, we created metamaterial with a negative index. That is not a big deal, because any metal below the plasma frequency, their epsilon value is negative. You all know that epsilon value is negative, any material. And these days, many of the TCO, that is transparent conducting oxide, or AZO, they have a epsilon value negative. And you know the refractive index is related with epsilon. Mu for non-magnetic material and all, we take 1. So if the epsilon will have a negative in a naturally occurring material, so this would also exhibit a metamaterial and negative refractive index. In a way, it can be. Okay, so there is there. And of course, we have a positive epsilon value. So our question was that, why if something is having a negative value, in a metamaterial, we have done the negative refractive index mostly. Again, this will help us in directing the rays and the traversing the path. Rather, it helped more for the transformation optics, metamaterial. But we people thought that it is only negative index. So it is not. Metamaterial can be a positive index, can be a negative index, it can be a zero index also. So I will be classifying the metamaterial like a negative index metamaterial, zero index metamaterial, positive index metamaterial. I used to give an example, like if you take an optical fiber having a core refractive index, say 1.5, and cladding refractive index 1.4. when the light is propagating through that fiber, an output you will measure its certain properties. Okay. Now you change the cladding refractive index. You make it as a 1.3. The output will be different. So the light's propagation characteristics, it does depend upon its surroundings more than the medium in which it is traveling. So in a way, that is also an artificially structured. Yes, that is also not available in the nature. We make it. So in general, I classify all those materials in which properties has been changed and artificially. So those are the metamaterials. So metamaterials will have a negative, zero, positive index. My talk is more limited to the zero index metamaterial. Okay, out of this. So I will classify the metamaterial. One is in the index type, another how it is made. So on the basis of constituent materials, that is metals or dielectric composite. As you know, the metal have a negative below the plasma frequency, epsilon is negative. Okay, dielectric is have a positive or zero. You have in an ordinary without re-engineering. So if you mix them, their epsilon value can be changed. So the composite can give you a negative refraction. Okay, so that is the one. Can give you a zero refraction, can give you another value of the positive refraction. So on the basis of constituent material, how metamaterials are there, metal and dielectric composite or all dielectric. That is an important one. As the drawback, I have told the metal is a lossy at this ohmic loss, it will be heated more and then there will be loss of the external energy incident in terms of the light on the basis of resonance also. So that is called the resonant and the non-resonant materials. Okay, that is some structure will be the resonant I will be giving you on the basis of the effective index also. So I classify the metamaterial in this way on the basis of the effective index, positive, negative or zero index metamaterial. Okay, the typical example maybe you must have already been given. You may say that how you will be wearing the epsilon. So if I take a coupled nano stripes made by the metal and dielectric, as you know, the metal has a epsilon value in the negative at an ordinary light and it's below plasma frequency. The dielectric has a positive. You mix up it depending upon the filling factor, how much of the metal, how much of the dielectric is there. You can change the epsilon value as much as you desire it. Okay, of course, it will depend upon the light which you are launching to him. Is it in a parallel to that or it is a perpendicular to that? They will find a different epsilon value, effective epsilon value, and the formula is very well known from these groups. Now, this was done mostly in 2000 to 2010. These periods are roughly I am categorizing. But later on, people thought to do it like in a dielectric, having a high refractive index or high value of a dielectric material, you incident light there. So there will be a dipole will be formed, electric field will be generated, and there will be a magnetic field. Okay, so depending upon its structure, how much the epsilon and mu will be there, one can show in this paper and see it that epsilon and mu can be generated in all four quadrants. That is, it will be positive, negative, 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 both are negative, positive, like that in all values. As you know that in a metamaterial, we look that at a particular wavelength, the both epsilon should be negative and mu should be negative, then we call that as a metamaterial, isn't it? But we can generate depending upon the incident of electric field, its polarization, and in this sphere's dielectric constant, one can generate all values of the En, epsilon and mu. So that is based on the constituent materials. Okay, so this is a metal dielectric composite, this is all dielectric. Okay, and the very one it is started with the split ring resonator. So mu effective, like a split ring resonator in between here, they work like as a capacitors. And thereby one can derive a formula how much will be the mu effective. It will be depending upon the radius and it will depend upon this width. And one can have a mu effective this. So we can make a mu effective of our desired value. We can also do, and they will be more pronounced at a particular frequency. That is why we are calling in the basis of resonant frequencies. They will give you this value. And similarly for wire mesh structure, we can do it in epsilon also, and thereby mu also. Here also there will be an electric field. So on this basis we generate it. So this is on the basis of resonance we can get it. Now on the basis of refractive index, maybe this is not given in the any book prior to few research papers. So if you have a positive index, let's say that this material, I have made it to explain that if it is a positive index material, Snell's law is valuable here, it's useful here. Positive index material, I allow to incident light. And this is a air, so it is a less refractive index, so the light will be going like this. If it is a negative index, that is this side is a negative index, light will be moving like this. Okay. And if it is a zero index material, what will happen? You launch the light here, you can use the Snell's law. So this is the angle it will be made. Okay, angle it will be more, we call that as an incident angle. So n1 sine theta, n1 is a 0. So whatever be the angle, n2 sine theta 2, that is the angle made by the normal here, that has to be 0. Okay, then only it will be satisfied. So from the zero index medium, if the light is incident here, it will all emerge normal to the surface. So that is the unique characteristics of zero index material. Okay, again this will be zero index material at a particular wavelength, so particular wavelength will be satisfying that. Okay, and nearby the wavelength will have a very less values of the refractive index, so they will give you accordingly the characteristics. Okay, so this is the classification. Okay, Dr. Tiwari, is it my voice as well as screen is very well visible?
Yes, sir, it is absolutely fine.
Okay, and I hope till now I am talking as a layman myself to all the persons. So now I will be explaining what is zero index metamaterial. Okay, so you know that this is a wave equation. Del to psi can be electric field, psi can be a magnetic field, and normally it is a 1 by c square. Okay, if it is in air, and d2 psi by dt is square. Okay, but if it is in a particular medium, it will be c by n. So n is square d2 psi by dt is square. Am I all right that this is the wave equation? Okay. Psi can be E or H, and a propagating wave will be given like this. Okay, propagating wave will be given like this. So if a medium is having a, let's say N1, if it is going to a denser medium, again coming back, it will be in denser medium, its wavelength will be different, smaller than in the rarer medium. Now in this wave equation, if you substitute, okay, so if n is reduced, this will be like this. Further reduced, it will be like this. Further reduced, that is when n becomes the 0. What will happen? This term will go to 0. And d2 psi will be 0. d2 psi is 0 means if I consider that as an electric field psi, then d2 of this, that is differential, second differential of the electric field, that is a spatial dependence of electric field, is a constant. That is, it is constant. That is in the zero index medium, there is no spatial variation of the field. It will be coming. Okay. If you take it from the solution, that is here k will become 0 because k is a propagation vector that you can write as a 2 pi by lambda naught. Okay, 2 pi by lambda. and then that you can write lambda is equal to lambda naught by n. So n will go up, okay, and therefore the k will be 0 in a particular medium. So n is 0, then k is also 0 here. So what will happen? The psi 0 will give this. So here from this we are finding there is no spatial dependence of the electric field inside the medium, but it will be varying with the time. Okay, in time domain there will be variation, but in a spatial domain it will not be. Okay, I will show to you, and this kind of things are there, then the wavelength will be infinity. Okay, because how will you wavelength? How do you measure wavelength? You measure from successive trough or successive this similar point like that. When you take it, that is the wavelength. Here it is not coming, so the wavelength will be infinity. So that is the wavelength infinity. Now let's see how the time domain it is varying. So you see the time domain it is like that. In the space domain it is not varying, but where it is being incident, that is varying. So that is what the solution is there. And this is a typical solution of the wave propagation. Okay, so here I have taken n is equal to 0.3. You see here the wavelength is encouraging. Here the wavelength is becoming infinity. Okay, so if it is a negative, what is there? This is metamaterials characteristics. In our mind, it has been fed that the metamaterial means negative refraction, which I say no, it is not like that. Zero refraction will be also there. Or anywhere you are engineering the materials, we are calling the metamaterials, isn't it? Okay, so here what is there? You see that if it is a negative, the wave is propagating along the z direction, but the wave vector looks like it is in the opposite direction. So that what will be there? It's a simple calculation. My job is to stick here. That is, as in the previous case, here, this one. So time variation I have shown you out. Space variation is not there. Okay, so that will be there. So zero index metamaterial, I will tell the physics also, but before that I am telling some characteristics. Okay, zero index metamaterial. I have taken this prism as a zero index metamaterial. Okay, it is done using the COMSOL. Some of my PhD students have done. Okay, so light is incident here. Okay, it is, so that is their electric. It is entering into the zero index medium, and this side it is not there, so it will emerge like this. Using the software you can design it. It has been done. So if it is going, means it is going to the normal to this surface, as we have done earlier. This is given in this paper also. Now, if this is a n0 Zi, any angle of light which getting incident here, they will be getting reflected, except the normal one. Except the normal one. Okay, it gets reflected. You can check that it will satisfy the Snell's law. Okay, it will get reflected like that. So it is not transmitting. Okay, here also you can satisfy. Now, if there is a normal incident of the light, what it will be? So it will be like that. It will enter, but it will be the normal to its component in all the side of the material. So the pattern you will be getting it like this. So light enters and exits zero index metamaterial at a normal. Okay, at a normal. So this is there. In other angle, it will be a reflector. So one can make a good reflector out of a zero index metamaterial at that wavelength in which it is giving you a zero index. There are other applications. A zero refractive index medium is the one in which electromagnetic waves do not undergo phase change. That is, once it has entered into the medium, there is no phase change. Okay, that is, the phase of the wave at the boundary of emergence is same as that at the boundary. The refractive index of the medium is given like this. Now you can make a zero. You can make a zero by taking any one of them zero, or both of them is zero. So suppose the relative permittivity is a 0, okay, and relative permittivity is a 0 for even naturally occurring material, okay, like say indium tin oxide, they give around 1400. I will give you that figure exactly. Their epsilon value will be 0, okay, and mu are not, so Z becomes infinite. So one can use this for the transmission if, like say, I make a very narrow, how much narrow? It is given in the research paper of this, and we can transmit the light from to here. We have to squeeze that zero index medium so that there will be connectivity here. One can show that around near to 100% light can be input in this by reducing this one. Now, if there is we call that as a ENZ material. Let me tell you, these days enough research is being done on ENZ material. Okay, this is naturally occurring also. We have an MNZ material also. So what will happen here, whatever be the channel, you can make the impedance 0 if you are making like that. Mu is 0. Or both is 0, then it will be an independent of the same, and you can couple from one place to the another. Okay, so zero index medium is basically called as EMNZ material. That is both epsilon and mu is 0 at a particular wavelength or particular frequency. Difficult to make. Okay, difficult to make. We call this ENZ material also two types. One is an ENZ material. ENZ material will have a epsilon value. The real part will be the 0, and its imaginary part, if it is very, very small, then that will also give us a nearly 0 index medium. So if its imaginary part is very, very small, and real part is a 0, then we will call that material as a NZI material. Okay, I'll just give you some example. That is not my part of presentation, but since I have taken the name, so naturally occurring ENZ material, let's not go with this, see the graph. This is a dielectric permittivity of indium tin oxide with a wavelength. They vary like this. At this wavelength, its value, it is something 1423 or something. Its value, the real part value is 0, imaginary part is small. So at this wavelength, we can call it as an NZI medium, and there can be many more advantage. Okay, that I will be telling you in this successive slides. I will be explaining that. This is not I am not kept as a part of my presentation, but just to convince the people that naturally occurring medium is also there. So that is there. So we classify ENZ material, and there is an advantage of that. Before going to the other advantage, let me tell you, many of you must have studied the laser action. So laser, you have a stimulated emission and spontaneous emission. Okay, we write spontaneous emission as a A21 coefficient and the stimulated emission B21 coefficient. So their ratio, that is A by B, is proportional to the N. Okay, N cube rather, N0 cube. That is in the medium, if the refractive index is reduced at that particular wavelength, then we can suppress the spontaneous coefficient very easily. Okay, so people are expecting that we will have a laser at a very less power. We call sometimes as a threshold less laser. Okay, so this is just, I'm giving an example here that ENZ material is this. Now coming back to, so these are certain characteristics of zero index material. I have to go how we can realize it. Okay, so I will be realizing also in the photonic crystal structures. Okay, but photonic crystal structure also, as you all know, maybe some classes must have been done. already for you, but I will explain what is a photonic crystal also here. So it is like this. What are photonic crystals? It is structures having a regular periodic refractive index variation in 1, 2, or 3-dimensional space. 3-dimensional space, okay? And this is a typical graph, we give it like that. There is a similarity between semiconductor. It has must been covered to you. I am not going, like said that this is the way I am giving you this presentation, like we have a structured like this. Okay, this is one N1, N2, N1, N2, N2 like that. So if you allow to incident the light here, what will happen? Particular wavelength which will satisfy this criteria, they will be reflected. Others will get transmitted. I have a video link. I can do that also to sharing, and the other will go transmitted. This reflected one, suppose if you keep similar structure this side also, and the reflected wave incident there, then they will remain confined and it will be forming a waveguide. So how much range of wavelength they are reflecting, that is called the photonic band gap region. Depending upon 2-dimension, 3-dimension, it is there. So here the reflection is taking place beyond this Snell's law. Okay, beyond this Snell's law. And this reflection and band gap you can tailor depending upon the dielectric contrast of the two medium, that is N1, N2, their lattice arrangement, filling factor, mode of polarization, TE mode, TM mode, and shape and the orientation of the constituent dielectric rods. So suppose if this, you will call the, okay, let me do it in this way. This is a photonic crystal structure. I mean a regular and a periodic arrangement. This is the diameter of the hole we are creating in a particular, I mean a dielectric rod here it is there. And this is the spacing, you call the lattice spacing. So you can confine the light, creating defect. Light can be confined it here, because in upper side it will see a one photonic crystal, lower side also it will see a photonic crystal. We assume that it is in infinites, okay, although that assumption gives you at some cost, it will not be exactly in the within the band gap region. Some band gap will be reduced. So light is incident, they will be propagating it here. We call that as a, it will be reflections. Okay. So just let me show those videos. Okay.
So you just play the video.
Yeah, it will be done. It will be done. Now it will be done. Just a minute. Okay. So, I mean, just a minute. I mean, I have, let's keep it like this. So this is a passing the light one. Now, let's say this is a photonic crystal structure. Okay. It is done using the photon design software. And now when you incident the light of a particular wavelength which has not satisfies the Bragg's law, that they are passing through it. Okay. Now you, okay, ये आपका, that is the guide, that is photonic crystal, the defect is created. So if you have launched the light is not passing here because they are getting reflected, I mean from here, and here they are acting in the above the photonic crystal. So the light is being guided here. Okay, So what do you find? Yes, in the nearby hole, some amount of the light will be there. Of course, their intensity and my electric field will be very small. So in that way, it will be there. Okay, so I believe things should be clear that I'm no. ये तो हमने this is that wavelength which is getting reflected. It is not passing. Okay, that is we have incident the light, it is getting reflected, not passing through. That is, this one is satisfying the Bragg's condition. Okay, so that is all. So that we have shown. So the photonic crystal is like that. Now, so photonic crystal, you have a separations like this, and then the lattice spacing. So certain photonic crystal will work like as a metamaterial, but so let me come to that. So I believe what is photonic crystal? I do not have to give this talk. So here it is a photonic crystal. So what wavelength? That wavelength is in the order of the Bragg wavelength, which satisfies their conditions. So it is there. Now suppose what is that is called Bragg scattering. This is Mie scattering. A scatterer is there. Its refractive index is M. So it will scatter of this wavelength. So this is a photonic crystal with A. Suppose if I reduce the A, then what will happen? The Bragg scattering wavelength will be reduced, but it is such a way that it should be, Mie scattering should be greater than this. Then it will work for that wavelength as a metamaterial. Or otherwise, if I increase the refractive index of this, then also I can make the Mie scattering more. That is, the wavelength will be more than their spacing. So at that wavelength, this material will be effective medium theory will be applicable, and the medium will work like as a metamaterial. So that is the basics about that. So that is the metamaterial. So I have explained photonic crystal, I have explained metamaterial, ENZ material. Now my job is to come to the physics of zero index metamaterial. Okay. One idea I have given you, if epsilon value can be negative for a given structure like ITO below the plasma frequency and it is positive, then at the plasma frequency, I can make the epsilon say the zero. Okay, so and epsilon is zero, thereby we can say that the one value has gone zero, so refractive index can be tailored at that wavelength that is zero. But people have studied this, study is around 2008, 2009 it started. Photonic crystals are distinguished from sub-wavelength structures used in the metamaterials. I have shown you here. They derive their properties from its band gap characteristics. The necessary condition for photonic crystal to show zero refractive index is the existence of a Dirac cone at the gamma point, that is at the center of Brillouin zone. What is a Brillouin zone? It is a unit cell of the reciprocal lattice. Okay, and then there is a point called the gamma point that here it will vary. This side positive, this side is negative. This is the gamma is equal to 0. So there the dispersion graph, this is omega k is dispersion graph, if comes like this plus another one, then we call that dispersion as a Dirac dispersion. And it is an accidental for particular structure, only it comes. And how this one is coming, very, very rare material or a structure it will be giving. This explanation is given considering a bit dipole and a monopole like that, but the mathematics and physics is like this. I mean, the wave vector k as a function of angular frequency in a Taylor series form about the Dirac point, I can expand like that. This is a wave vector. Okay. It will be like that. This K dash is dk by d omega at at a Dirac point that. Okay. So at K point here, this one is a 0. Okay. So this one value is a 0. So if this is a 0, then K omega will be, if other higher order value, if I neglect, which is I neglect means you can differentiate, do it, its value will be much more smaller, so one can neglect it. K omega will be coming like this. Okay, omega d is the Dirac frequency, that is from here to at this point of frequency, and K omega is in this direction whose 0 value is here. So if I operate this structure at omega less than omega d, okay, the wave vector will be giving you like a negative one. How? You can say that you can relate this also with refractive index. This will be 2 pi by lambda 0 into n. Okay, so n will be giving you a negative. So here, if you operate at omega is equal to omega d at one particular frequency, it will give a 0. Other frequencies higher than this, it will give you a positive. So this is the basic origin of the materials to exhibit the negative, 0 refractive index. Criteria is that its dispersion graph should follow the Dirac dispersion, and its surface is like that. This is one surface, this is another surface. Two Dirac cones are there meeting at this point at K is equal to 0. How we get it? So if we take a photonic crystal made up of the silicon rods having a epsilon value 12.5, arrange them in a square lattice, okay, and the rod's radius is like this, that is related with the lattice constant. I will show you that it will give you only at this dimension the 0 index. If you vary how the cost will be there, we will not be able to get the Dirac cone touch to each other and 3 bands, one parallel to the surface and 2 perpendicular to that will be coming. It will not be coming. So if we take this kind of any structure, that will give you the band diagram like this. This is the band diagram. These are A and all lambda. So here they meet. So corresponding to this value of this frequency which we are telling, isn't it? It will give you the negative refraction. This is the dispersion surface has been plotted that for the structure given. That is not my work. I have been referring that paper. So at that one can also make in a simpler that, like you are assembling the silicon rod, you can take a silicon wafer and you can make a hole using the electron beam lithography. It will be CMOS compatible, and its hole size, how much should be there, how much should be there, is given in this paper roughly with this dimension. Then this structure will also give the refractive index 0 at 1550 wavelength. The previous structure also gives the refractive index 0 at 1550 wavelength. Yeah, some people may ask that we will not be get an absolute one particular wavelength. You are 100% correct. When you are generating 1550 micron light, nanometer light, there will be plus minus adjacent light will be there. So the adjacent one will have a less refractive index value, near about that, but exact 1550, they will be experiencing the 0 refractive index. So this is our work. We have been, got inspired with this structure. So to me, it also looks like this structure. That is what we have taken. We have taken a silicon slab, assembled them in this manner. One slab here and here. These are the slabs. Okay. This is like a hole in a silicon. So I have done with this silicon slab assembled in this manner. Of course, it has a certain width of this slab. Its dimension is there. And we have derived what should be the A, what should be the W. and of course the silicon's permittivity, at what wavelength this structure will be giving me the negative Dirac dispersion cone and then negative reflection. So this structure is optimized for exhibiting the 1550 wavelength. The previous one is structure and all also worked on the around 2017-15 like that. We have also done this in this structure. So their photonic band structure is coming. For TM mode, it is like this. For TE mode, it is like this. Okay, there is a slight change in the structure. I mean, same structure does not work, give the zero dispersion for both the mode. Slight changes we have to make. So that is given in there, like W by A 0.22 we have put it. W is the width of that slab. So it is there. At this one it is giving, and this is giving at W by A at 3.0. Almost both of them are designed for TM mode and TE mode. They will exhibit a zero index criteria. Okay, so their unit cell has been taken like this. What we have done is a typical what has been suggested by D.R.S. Smith's, that is Penry's student, the electromagnetic parameter retrieval. We have given an input wave. So S11 is a reflected, S21 is a transmitted one. Output we have measured it. So S11, S21 we have found for the different wavelength, you can say that. Okay, use this formula and obtain the value of N, Z, impedance, epsilon, and permeability. Okay, and this is given for such a structures only. So the formula was used, call this, and when we plot for TM mode and TE mode with S1 and S21 parameter, our graph comes like that. One is for N, epsilon, and mu. So that is, you see that 1550, 1.55 micrometer, they are giving the zero refractive index. So effective material parameter calculated for TE polarization and calculated for the TM polarization. So you see that the nearby wavelength, that is, as I said, that 1550, when you are generating, you have a 1552 also and 1548 also. So they will also have a bunch of bit lower refractive index. Okay, lower refractive index. So my point of saying is that in a structure where you want to make a lasing action and you are operating at these wavelength, then we can suppress the spontaneous emission much more easily. Still, very one or two research paper has come. People are working on that. Okay, so the zero refractive index has a multiple applications. Okay, including in a non-linear optics also. So once we have made zero index, I am claiming that my structure is giving a zero index. We have to test it. So we will verify it by using this Snell's law. Okay, so that is the same structure has been put it. Okay, put the light incident, output light will be coming light. These are all theoretical modeling done using the console. Of course, I have not done it. My doctoral students have done it. Okay, for each structures. So what you are getting at output, this type of a light. So divergence of angle, that is, this angle is very, very small, around 1.7 degree. So near about this light is giving you a normal incidence at the output surface, indicating that yes, the parameter you have selected is yielding a zero refractive index at 1550 wavelength. Okay, so that is the verification by Snell's law for both TE polarization, for TM polarization also. Okay, now let's do with the some other structure. This also a structure we have selected almost similar. Again, this is a silicon rod. Earlier I have taken as a silicon slab, and then we have done, I believe slab is a more general one than taking the rod. Okay, than taking the rod. It has no mechanical structure, but most of the zero refractive index are done with these parameters. We have followed it. Our earlier paper is with this slab. To me, that looks more practical than this one. But again, we need to prove that yes, the zero index is coming. So we have done it. Again, this is structures. Also, you calculate the dispersion, photonic band structure. Okay, the band structure is coming to this. So you are taking a silicon rod having a epsilon value 12.5 at that wavelength, lattice spacing 840 nanometer, rod's radius is 0.2. So something it will be coming around 180 or 200 nanometer, whatever the radius of this will be there. So if you calculate photonic band structure, it will be like this. So that gives you the Dirac point. Okay, that gives you the Dirac point that indicate that that structure proposed by us is giving you a zero refractive index. Now let's see that if I don't do R by A 0.2. Okay, so if I am slightly varying, like say 0.18, I am unable to get this kind of a convergence in the dispersion graph. So it is very sensitive, and that is why it is called accidental degeneracy. That is, एक structure में तो आ गया, सभी structure में नहीं आ रहा है ना? So one has to study more carefully about the different materials, permittivity and their condition to obtain that. In a silicon structure, it has come like that. So photonic crystal having a particularly chosen R by A ratio, 0.2 in this case, but may have a different value of a different dielectric, can fulfill the condition of a linear dispersion around the gamma value 0. For any other value, the condition fails and Dirac cones are lost. The structure can be tuned to different wavelength. The one varies the periodicity without disturbing the ratio of R by A. Now, one can make a different material. Like here, I have taken a silicon rod. I have assembled. In between the medium was air. So air means refractive index 1, we have taken 840 nanometer. But if the medium is filled up with the another material, or you can say you can take a sensing characteristics with respect to the refractive index. Okay, refractive index. So if you put a 1.2 refractive index, your lattice spacing should not be 840 nanometer, it should come to this value. If you take 1.4 lattice spacing in order to yield a zero refractive index. So you can obtain the generalized graph that is at a different wavelength. Also, if you want to have a zero refractive index, then using these structural parameter, one is A by lambda, this is R by lambda. Okay, R by lambda. So you can obtain what should be A, what should be R at a particular wavelength where you want to make a zero refractive index. So a structural dependence, one can get it. Again, from the same parameter, we use the S21 that is in a transmission characteristics, because in the formula it is there, and the phase how it is changing. But S11 and S21 parameter, we have calculated these structures also. It yields at 150-50 the zero refractive index. Okay, just 1 minute. I will take a break. Okay. Okay, so I'm back now. So this is the slide which we were doing. Am I all right?
Yes, sir.
Hello?
Yes, sir. It's fine.
So one can design at this. Now, once you make a zero index, what are its application? Okay, so that is also we want to So homogeneous zero index slab, material slab, to play the role of highly directive antenna for an omnidirectional source. That is, you have kept a omnidirectional source here, let's say LED or diode, which is not giving in a one particular direction, it is open. Maybe you can say a bulb type of a thing, light is coming like this. So larger amount of the radiation emerges out from the larger side of the surface. That is, if you plot its electric field contour, it will be like this. This is also using the COMSOL plot. This is in the polar diagram. The electric field associated with that, they will be giving you, if you reduce this size, it will be giving you like this. Okay, so we will be measuring. So what we have done it, we have measured taken the dielectric rods, that is a silicon rod, as the structure I have given 840 lattice spacing nanometer and the 0.2a radius, and this is 3x7, that is 3 rows or 7 columns or whatever is there, it is these 7 structures is there. Okay, and in between a source is kept. Okay, the light will be of course emitted in all the direction. Okay, and if these slabs are not there, then the output pattern will be like this. If without all this, it will be like this. So what I am doing, I want the light should come in a particular direction antenna. This side we have put a silicon slab as a Bragg reflector, with a calculated values of the separation between them. So any light which is going in that side, that will be reflected back in the front side. And from this side, we consider compared to this, the dimension is more, so less value of intensity of will be there. So radiation pattern of the emitter will come like this. And if you plot its directivity and all, one can increase the directivity. You can do in the other direction also Bragg slabs and get the light output from that in a particular direction with a higher value of the directivity. Okay, so that is the one, that is applications of the zero index. Now let's say that I am saying that this is the values of the structure you will be doing it, how to show it experimentally that the refractive index is 0. So that was done by this RESAF group in a Harvard University. I know with Eric Majur's group, he is his postdoc student and all. They have done a structure. That is, this is a silica structure. This is a silicon structure. And silicon, they have calculated the holes. That hole was done using the E-beam lithography. And in between there is no hole. Here is also photonic crystal structure. Here is photonic crystal structure. So here it will act like as a waveguide, that light will be moving. So what they have done it, they have designed that it should give us a zero refractive index at 1625 nanometer. Okay. So they input the light wave both sides. So if they start with say 1575 nanometer, where there is no zero refractive index. Okay. So there will be an interference pattern, that is a standing wave will be formed in between. A standing wave will be formed means there will be a node and anti-node. Okay. So if they are away from zero index, then the nodes are formed with a less separation. As you approach towards the zero index, the number of nodes is reduced. Very good intuitive ideas to prove that. And as we approach to 1625 nanometer, what happened? There is no node. This is, I mean, the node separation is infinite. That is, the wavelength is getting infinite. There is no perfect nodes and anti-nodes. So they observed this. This is directly from their paper, but one can simulate. I will give you our own reference. We have designed similar structure for 1550 nanometer. We have taken the whole size 183 nanometer and the lattice spacing something called 582 or 83 some nanometer, and for 1550 nanometer It has been designed, simulated, and we have presented that somewhere, that structure, but this is the structure. So one can show the existence of zero refractive index within the lab. So that was the first experiment, and that led the interest the people to increase in working in this. Now the another good example is the electromagnetic cloaking. Okay, electromagnetic cloaking, that is very much important. Cloaking, you must be knowing that what happens, some material we want to keep in between and no light wave can pass through that. So that is done through the transformation optics, that is we use the negative index material. So any light is coming, that light is bent and it goes from the periphery of that side's medium. So it will appear that as if nothing is there in this medium. So we design a zero index. Another way is that you should design a zero index material and there you keep the items to be clocked. Okay, so this is a zero index material. Now in between we have kept a material. These are all simulated graphs using the console. We have put at a 1550 nanometer material, isn't it? So light wave has put it here. What will happen? They will go like this. The one which is coming here, if it is a zero index medium, what will happen? It will come here, that 1550 wavelength. It will without disturbing this. So here the pattern, there will be no shadow will be formed. The light wave will be like this. Okay, you see, if it is not zero index medium, it will be a shadow will be formed like this. Okay, so zero index medium is another application is for clocking, and clocking with a much more efficiency than what people use using the transformation optics. Okay, now coming back to the wavefront engineering. So what is if I put a zero index medium, that is I am calling EMNZ medium, that is mu is zero, epsilon is zero, both. Okay, and there I make a slab like this. So when the light wave is incident, again it is a zero index, so only the normal light will be entering, no other light. Okay, normal light will enter. You can check that using the Snell's law also, it will be satisfied. Okay, so when the light wave is coming here, they all will be in the same phase in this pattern, because here is no variation into n. So n into x variation is not there. So whatever the way it is coming like this, so their pattern will be changed like that. That is, whatever the wave front was there in the plane wave front, we have made it in this wave front. If the EMNZ material is made like that, then the wave front will be like this. So we can engineer that. Okay, so that one was there, the work done. So we also tested using our structure, which I have said that the silicon slab making, and put it there. So light wave is incident here. Now the wave front, you see it is like that. So that is a Venn type of a structure, like a Venn club or mix at a junction. So that kind of a structure it is there. So you get is this. So this is the another application. Okay, another application. So let me tell you about. So zero index medium is giving another direction. Okay, that is emerging area kya, what are coming. So another area, I do not know whether you people have heard it or not, photonic doping. Okay, like electronic doping in a silicon, you dope a germanium or in a material and you get its electrical property change. So we want in a particular material to dope so that the optical property should be changed. And again, the doping means not like making a photonic crystal. Only one inclusion should give you a desired property. Okay, or two inclusions should give you desired properties. Okay, so people are working on this called the photonic doping. There are reports that if you make a zero index medium and there you dope certain material, so by doping only one, you can get many functionality changed. Zero index based non-linear optics. Okay, in a non-linear optics, particularly second harmonic generation and all, the efficiency does depend upon the phase matching. Since here the phase remains constant, it is matching is easier. Okay, and also it is done at that particular wavelength, if it is giving you a zero refractive index, efficiency of second harmonic generation, this is already reported work, is much more increased compared to the our conventional thinking. I have given you a briefly threshold less lasers and optical sources, that is emitter. At a low power it should give. So where the lasing action is done, if you get it done in an optical means, pumping in an optical means of that particular wavelength of the light, which is experiencing a lower refractive index. So as I said, A by B is proportional to N0 cube. So if that N0 is the medium refract, if N0 at that particular wavelength is very, very less, like earlier you had a, let's say 2, and now you are making a 0.1 also, then their cube, so many more times the spontaneous emission coefficient will be reduced, 1,000 times. So it will be like that. Now people are doing with the coherent thermal radiation. So in a zero index medium, they will be inputting some heat source, and where the heat should transfer, that they are taking. Another people are doing is called the metatronics. Okay, some research papers have come, like how to take a circuits, optical circuit, using zero index material, metamaterial, negative index, positive index, so that when a light is launched, it should work like a capacitor, it should work like a resistor, or it should work like as a inductors, so that all circuits can be made for based on the propagation of the light. Now coming back another, that is called doing maths with light, that is called informatica, optical informatica. As you know, what happened, we can say like a Fourier transform, when the light is moving in the fiber, and at the output you measure the light, you called it a far field pattern. You called it as a far field pattern. Far field pattern is nothing but the Fourier transform of the near field pattern at the exit. So in a way, the light is doing some kind of a mathematical function. So here also, within the zero index material, if we dope something, or in a normal photonic crystal, if you input some light wave, it will have some function. And output function will be as we desire. If we want to integrate, integral equations can be made, again with the interaction of the light wave to the materials. Okay, so the light will do the mathematics what we require, be it in a Fourier transform, or be it in addition or subtraction. So these are the ways we are going towards the zero index photonics. Of course, in between we use the other types of engineering material. So this is the one which I wanted to tell. I believe I am well within the time allotted to me. So I just summarize my presentation. That is what I have given you. I have given in my own way what is metamaterial and its classification, particularly classifying in terms of the refractive index. To learned readers, people like us, many of you, they think metamaterial means negative refraction. Okay, so we have to educate them also. Sometimes it is difficult to unlearn a concept than to learn it. Okay, so that is what is happening. So zero index metamaterial is also belonging to that. It was very obvious, but somehow people have not worked. We were more curious to show it in negative refraction, and whole books and books came with the metamaterial. But equally good, fascinating devices can be made using the zero index metamaterial. So many of zero index of optical materials and devices can be formed. And I have presented in a metal and dielectric, making it a bit easier than all dielectric. So all dielectric zero index metamaterial is structures and conditions for Dirac point and classifications of ZIM. And I have given you the applications of zero index metamaterial as an optical nano antenna, electromagnetic clocking, wavefront engineering. Of course, there are many more applications. So ZIM is giving a new directions in photonics, one step ahead. Okay, so I believe the major references which I have been reading and using is this, that is experimental realization of epsilon near zero material at a visible wavelengths. Okay, epsilon zero, as I said, given you graph, and ITO at a 1400 nanometer was already there around. So in the visible range they have realized in a Nature Photonics, most of them are presented that. Moitra's paper, very active researcher in this, realization of all dielectric zero index metamaterial, on-chip zero index metamaterial, subsequent development. And this is a near zero refractive index photonics, a review paper by these. They are one of the pioneer in this. And of course, since I have worked this in the last few years, along with only one doctoral student, so we have come across a book. Our book has been published in this year only, called Zero Index Metamaterials, okay, Trends and Application. So these are the major references. One of the Nature paper. This is our own book. Believe me, I'm not doing a marketing of our book. You can start reading with a Nature Photonics. But in the book, at a one place, I have started this, the origin of a refractive index, and how with a minimum reading a student or a researcher wants to do the work. So it is a only 145 pages book, but almost the latest items have been given. So our idea of writing the book was there so that a reader should not read more of details about photonic crystal and the other metamaterials to come into this. So that was there. So this is all about my presentation and major references. I must acknowledge the PhD students and postdoctoral students working in my supervision, both at a CSIO and DTO. Is still some people are working, and some of the financial support which I have got from the BRICS project and Indo-Russian project. There are very good group in Russian groups. Of course, the metamaterial is started from there, and some project funding through the CSIR mission project on meta surfaces. And this, I present you all a bouquet made up of photonic crystal fiber and photonic band gap fiber. To thank you for listening me. I will be open for question, and that is why this mic is presented here, so that you can ask me the question and I will listen to it and try to answer. If not, we will read or you will yourself. Am I all right?
Yes, sir. Yes, sir. Thank you very much, sir, for a nice talk, and it is really very informative for all of us. So the questions, please.
Okay, now I am opening my figure also, picture also, video is on. Okay. So I have completed in 1 hour 25 minutes.
Yes, sir. So there is one question from Sanjay Sharma. He has written in the chat box that can we make n effective equal to the actual value of n of a material?
Can we make n effective equal to the value of n of material? I think what he is saying, like refractive index n, whatever somebody has defined, like the silicon's refractive index H, something what we call 3.3 or 3.4 or 3.6, whatever is there. So that is they have defined, assuming that it does not change with respect to the wavelength, isn't it? When we have taught the students, we have created the problems. In the 10th class, we have not said, we have told them the refractive index of the glass is 1.5. We have not defined. Actual definition should be refractive index of the glass at 1.5 at this wavelength. Okay, and from which medium you are looking at. So that is the original. So the value of n given which we are seeing n is assumed that n does not change with respect to the wavelength. Yes, there are material in which they do not change for a wavelength considerably. Okay, so for that you have to, I will say ki n effective at a different wavelength it will be different, and different structure it will be different. Okay, but it will vary in around that. But if you want to read it in a more grasp the idea, read the Feynman lectures of physics book, as well as the book by my own teacher, Professor Ajay Ghatak, Origin of Refractive Index.
Yes, sir.
Okay.
So, any other question? So, Sanjay, do you find your answer?
Or otherwise, he can tell the himself answer.
Yes, sir. I got it, sir. Thank you, sir.
Yeah. Okay.
Thank you, sir. Thank you, sir.
Okay. So is it all right, Dr. Akhilesh Tiwari? It's over?
Yes, sir. Yes, it was really absolutely very nice talk, and it was very informative for all of us, because you have started from very basic, and all of us who have no idea, even for us, the zero index material is a new kind of material, because the negative index material is very popular and everyone is reading in papers, but zero index material, I think it's a little more, and its applications are also coming. So now we have an idea what is the blend of photonic crystals and metamaterials, a different kind of metamaterials also.
Okay.
So thank you, sir. Thank you very much for your giving your time to us in this ATAL program, so that we have opportunity to listen to you. And thanks a lot, sir.
Okay, thank you.
There is one more. Ankit, are you asking some question?
Is Dirac point totally accidental? Yes, here's a question. Is Dirac point totally accidental? Now I will not say totally accidental. In the beginning, those who have initially worked for a particular structure they have got. I have given you that if you change the material in that, now we can design it. In the beginning, they have got that a particular structure, like I have shown you, R by A is equal to 0.2. Structure wise, only at that structure is giving. These days, people have explained it, and we have worked that if the medium changes in between, so it is not that R by A 0.2 only it will be coming. Other point value it will be coming. So first time they have called it accidental degeneracy. Now we have got the idea of when it will be coming. So it is not accidentally in true sense. Am I all right?
You are trying to...
Sir, actually, I have a question.
Yeah.
Thank you so much, sir. That is, the talk is very much basics and very much informative for the beginners. So I am new in the field. Sir, zero index material, as I understand that the optical resistance of the material is zero. So that is called zero index material, or is any other kind of thing?
I have promised in the beginning of the talk that I will give you a new definition of refractive index. Somehow I have not given. Now you asked me the question, I am giving you that definition. Okay. I give define like refractive index. The refractive index is the resistive and impulsive force experienced by the light wave of a particular wavelength when it enters into a medium. This definition you will not find in any book. Of course, you can challenge me in some sense. That is why resistive and impulsive word I have used, because somebody has questioned me. Because when the light enters into the medium, it remains in the same velocity.
Yes, yes, yes,
Okay?
sir.
That is why I have used the impulsive. That is when it is entering into that. And why I am finding it is like this. Say when you put a laser light on, so it is in the air, it is traveling with a c velocity. When it is entering into the medium, its velocity becomes v, rather reduced. So
yes.
I say that the momentum of the light is changed, and change of momentum is nothing but a force. And since it is reduced, I am calling a resistive force. Again, earlier I was defining as a resistive force, but somebody has questioned me, once it enters into the medium, then it is not. It is like that. So I am correcting that it is the light, it is resistive and impulsive force experienced by a light wave of a particular wavelength when it enters, propagates in a medium, enters and propagates. Of course, for God's sake, do not write this definition or tell the teacher when they are asking you a question. because everyone has studied that the refractive index is equal to C by V, or the angle of incidence and angle of refraction. Okay, I wish that I should write a big paper on defining my own way of the refractive index. Dr. Upendra, you are convinced with my definition or not? That must
No,
have
I was totally convinced, sir. Actually, my question is towards
इसमें
the
एक और चीज है, यदि
Yes, sir.
ग्रुप वेलोसिटी कैलकुलेट करेंगे तो ग्रुप वेलोसिटी इनफिनाइट नहीं होता है, फेज वेलोसिटी इनफिनाइट होता है. You know
Yes,
that the
yes.
phase velocity, so phase velocity will be infinite. So it is does not mean that कि आप एनर्जी ट्रांसफर कर सकते हैं with respect to higher than the c velocity. Einstein is still correct. Okay, is still correct. My other topic of research work is just slow light, isn't it? Generating a slow light. So yes, phase velocity के लिए कोई resistance नहीं है, which you are saying it is like that in a zero index medium, because हमारा phase change हुई है.
Okay. Yes,
Is
yes,
it
yes.
correct? Are you satisfied with my answer?
Yes, 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 sir.
Okay.
Thank you, sir. Thank you again.
Okay.
So
Yeah, if you have to ask any other further questions, I am open. You can send me by email. I will reply.
Yeah. So anyone have any kind of question, please write to us or directly to Professor Sinha sir, and certainly he will answer later on also. So thank you, sir. Let's thank again Professor Sinha sir. So for a nice talk and his interaction with us. Thank you, sir.